you. Let me start by thanking the organizers for the invitation to speak. It's a pleasure to be here. And I'll be talking about resurgence, negative tension branes in the context of large N duality. So this is work done mainly with my students. Some of them are actually here, so if you want to talk to them about these things, you can. Stuff that appeared past couple of years, and some stuff we're writing up that hopefully will appear by the summer. All right, so the main goal of this resurgence program is to see how much mileage can we get out of perturbation theory into trying to construct non-perturbative string theory. So I don't think I need to tell anyone in this audience that string theory is generically defined perturbatively in powers of the string coupling GS, and it's a sum over general, right? And the free energies at genus G, they grow factorially fast. So this perturbative series is asymptotic. Now, that might seem annoyance at first because, you know, it has zero radius of convergence, but we know that actually this is great because it's telling us that there's a lot of non-perturbative stuff hidden in this asymptoticness. So on top of the monomials of the perturbative string coupling, I also find non-perturbative stuff. These are the transmonomials, exponential of -1 over GS. And so we would like to dig these guys out, sorry, one too many. I would like to dig these guys out of perturbation theory in order to have some sort of non-perturbative construction of string theory. And the key word here is construction, not definition. But for that, we need to have the perturbative expansion under control. So the first question we may ask is, when is this possible? So in the spirit of this program, here is one perspective on what string theory might be. Of course, it's much more than this. But at the very least, for this talk, it's an asymptotic solution to some random matrix models where I can actually have perturbation theory under control. So we know this since the 90s in multi-critical string theories, through the thousands in minimal string theories, and the Hermitian matrix models and their relations to topological strings until more recently in JT gravity. So the advantage of working in this setup is that I no longer have to be bound to CFT worldsheet where going, you know, past genus 2 is hard. I know I have other tools at my disposal that will allow me to do computations. I have string equations, which come just out of the matrix model, the topological recursion that comes out of solving the loop equations, the holomorphic anomaly when I do the connection to topological strings. And all these tools are very good both perturbatively and non-perturbatively. So, okay, we would like to go back to our goal. Can we have some non-perturbative construction of string theory in this setting? And so we should use resurgence to dig deep into the perturbative series and try to, you know, come up with all the possible transmonomials that are going to give me the non-perturbative answer. So, so what is resurgence? We had a program here at KITP 7 years ago, you probably recall. And so if anybody's interested, there's some introductory talks. For the purpose of this particular talk, I think I only need 2 slides. This is one of them. So basically, here's the goal of what we're trying to do. So we start with our asymptotic series. These are the free energies, which are growing factorially fast. And I do a Borel transform. Basically, what the Borel transform is doing is cutting the factorial growth and is transforming a formal power series asymptotic into a convergent power series at the origin. And then you'd say, okay, let me do the dashed arrow and just invert the Borel transform. That's a Laplace integral, and which I can do along any ray on the Borel plane, and that's the answer. Well, not so fast, because there are singularities. So this Borel transform is not entire on the Borel plane. If it was entire, that would just mean that the series I started off with was not asymptotic. And so there are singularities at, let's say, omega in the complex plane, which are of this type. So this is a restricted class of functions known as the simple resurgence functions, whose singularities are all logarithmic. And we can work in this class because, at least in the examples that we've been doing, that's all that shows up. So all singularities are logarithmic. There's some holomorphic stuff I don't care about. And then in front of the singularities, there's also some other holomorphic content, which basically amounts to what's in this equation. So there's some coefficients, which for the purpose of this talk are just Stokes data. And then there is some function here, which turns out to be the Borel of something else. And that's why we call this resurgence, because at the omega singularity, I see the resurgence of the omega sector as the Borel of that sector which appears in front of that log branch. And then I can do the Borel Laplace resummation as long as the ray of integration doesn't go through omega. If it does go through omega, then I have Stokes phenomenon. So here's a bunch of singularities, and there is now going to be a difference between doing the Laplace resummation on the left and on the right. And the difference is just the sum of these Hankel contours. It's not too hard to do the calculation. And here's what we get. We get Stokes data, we get our transmonomials, and we get the resurgence of these people. So all sectors must be included in the full solution. The perturbative series is not enough. And this is basically, in 2 slides, trans-series and resurgence. Now, it turns out that there's a particularity with the string theoretic expansion, which is it's an asymptotic power series, but in powers of the string coupling square. What this implies is that the Borel transform will have fixed parity. So on the Borel plane, here's a picture on the Borel plane. This is a numerical simulation of these singularities in the example of JT gravity. It's not important what the example is because this is generic. It's just because we can make a nice plot. And the blue dots are the Borel-Paddy approximations to these log branch cuts, and the red dots are the singularities. And what we can see is that the singularities on the Borel plane are symmetric. So in the resurgence literature, this goes by the name of resonance, and this is completely generic to string theoretic expansions, at least in all these models that we've been looking at. So the question is, well, these singularities are associated to some sort of non-perturbative content. What is it? Because I have a positive singularity and I have a negative singularity. So what would each one of these correspond to? So let me straight off give away the punchline of this talk in these 2 next slides. So we have familiar non-perturbative corrections. These are associated to that singularity, to the positive singularity. So this is very well known since the 90s. So in the matrix model context, these are terms of the type exponential of minus n. They're associated to eigenvalue tunneling. So here's a picture of the spectral curve, say, of the cubic matrix model. It's got 1 cut. It's got a pinched cycle, which is my non-perturbative saddle, and it's got 2 contours. And if I do eigenvalue tunneling through the standard physical sheet, then I get the contribution e to the minus n. If you do the calculation in string theory, you have D-branes. This is just a cartoon. And you have e to the minus 1 over gs. So that explains that singularity. What about the negative singularity? Well, it turns out that it also has actually a very simple explanation. So in the random matrix context, this is associated to anti-eigenvalue tunneling. So instead of removing an eigenvalue from the cut and putting it up there at the singularity, I do the same, but I do it on the involuted sheet, because remember that the spectral curve is a double cover over the complex plane, at least for the one matrix model that we'll be doing here. That will lead to a contribution of that type, exponential of plus n. And in string theory, basically, again, this is a cartoon, we're just going to get terms which are of the type e to the plus 1 over gs, which are negative tension D-branes. Now, these negative tension D-branes are nothing new. They've been studied in the literature quite a bit. But herein, what I'm trying to tell you in this talk is that they're a requirement of resurgence. So you can't basically do without. All right, so here's the plan of the talk. I will tell you why resurgence tells you that all these sectors must be there. This comes out just of trying to solve string equations. Then once we realize that all these sectors are there, I'm going to try to explain what is the story of eigenvalue and anti-eigenvalue tunneling. How can I have a physical interpretation of these terms from matrix integrals? And then the same from D-branes. They'll all end up with a comment. All right, so let's look at what happens with string equations. So we've solved many different examples, but in this talk I'm just going to focus on the simplest possible one. It's only half an hour. So we'll focus on the Paulin-Villon equation. So that's the Paulin-Villon equation. It's a second order nonlinear differential equation. For U is the specific heat of the 2,3 minimal string, which relates to the free energy in this simple way. And Z is basically the string complement, just whatever. And it's been known again since the 90s very nicely how to set up the perturbative expansion of this string theory, and people have done a lot. I mean, there's gazillions of papers on this. More recently, in 2010, people started studying the asymptotics of the instanton sectors, not just of the perturbative series, but of the instanton sectors. And in studying, I mean, this could, you know, in fair detail, this could have been seen in simpler settings, but this is just historical context. It's what happened. In studying the asymptotics of the 2 instanton sector, people found that, hey, hang on. On top of the standard instanton action plus, I also need the instanton action minus to properly describe the asymptotics of my 2 instantons. So what this implies is that the full solution for the specific heat is not just going to be a perturbative series. It's not just going to be a perturbative series with exponentially suppressed stuff. It's going to be a full trans series with both exponentially suppressed and exponentially enhanced stuff. Okay? So that's the, let's say, complete non-perturbative answer for the specific heat of point level 1. And let me just tell you what are the different ingredients. I have some asymptotic power series. I have a lot of them of this type. I have some log sectors. The log sectors are really not relevant. They're not independent, and they actually resum, so I'm not going to care about them. And I have the exponentially suppressed and the exponentially enhanced transmonomials. And then I have trans-series parameters. What are these trans-series parameters? Well, I'm solving a second-order differential equation. I'm expecting to have some sort of, two boundary conditions, two initial data. So that's what they account for. That's one thing that they're there for, but that's not the only thing they're there for, because they also are main players when Stokes phenomenon takes place. On Stokes lines, they jump. So even if you set them to 0 on your little wedge of moduli space, because I don't really want to have any transmonomials around, or as I go around the complex plane, they will be turned on. All right? And let me just make this comment, there's this funny thing that when n is equal to m, all these sectors have the same weight. And basically, they're non-perturbative, but they don't have a transmonomial associated to it. All right? So again, this is the generic structure. We've studied many examples. We've solved a few multi-critical models, a few minimal string theories, a few matrix models, JT gravity. And of course, the higher the string equation is, the higher dimensional this lattice of trans-series sectors is going to be. So I'm always showing the example of Conleville, where it's basically two-dimensional. And the generic structure of the solutions is of this type. So I have my perturbative series. I have what we would call multi-instantons. I have these guys that the resurgence is predicting. What are they? I already told you, but we'll come to the computation. And then I also have these guys, which are non-perturbative, but they're standard of order GS squared. So what are these new resonance sectors? Which is what I will explain next. Well, so let me just do 3 comments on top of this, just things that I will not talk about, but I think are worth being commented, which is, the first comment is that this is not the full answer. If I just give you the trans series, you're not done. So you also need Stokes data, because you need to account what happens as you move around the complex plane. Stokes data is complicated, so I will not say anything on Stokes data, except it has been computed. It's an infinite number of numbers, for which we have generating functions that basically depend on 2 numbers. They can be computed directly from matrix integrals. They can be computed directly from boundary conformal theory. I will not say more about Stokes data. The second comment I want to make is that these things have been extensively checked. I mean, this is not supposed to be a legible slide. It's just to convey the idea that we've done many numerical checks, and everything checks to, 100 digits. So we're sort of convinced this is okay. And the third comment is that, this is sort of well known, that there's always 2 guys. It's been known in the mathematics literature for a long time, but also in the physics literature. This is the first paper I could find. Maybe there's earlier, but the first one I could find is 1990, Douglas and Schenker, where they do have the 2 exponentials, but they take an approach which I will not take in here. So I'm not going to kill anyone. And we're going to take the both exponentials along for the ride. So that's the structure that we would now like to explain. All right. So the first attempt at explaining this is from matrix integrals. All right. So how can a matrix integral describe a specific trans-series sector? So I'm writing the trans-series again here. Now for the partition function. And I will use Roman notation for stuff that I computed out of a string equation. And those are the sectors, Z and M. Those are the positive and negative exponentials. And those are the trans-series parameters. And I'd like to reproduce these sectors from a matrix integral computation. So I'm using curly Z for stuff I'm computing out of the matrix integral. So that's the matrix integral, which I write in diagonal gauge. Lambdas are the eigenvalues. That's the van der Maan. And what I'm expecting naively to say is that, well, depending on the integration contour that I pick for the eigenvalues, I'm going to get different trans-series sectors. So how do I do that? Which eigenvalue contours correspond to which trans-series sectors? Which eigenvalue contours that then I can evaluate through saddle point. Well, for the standard multi-instantons, this has also been known for a long time. I'm not putting any references because there's literally gazillions of papers on this. And so the way this goes is basically the following. So from the trans-series point of view, I have, say, the perturbative contribution, and I'm looking at the discontinuity associated to the Stokes, or if you want, to the positive Borel singularity, the Stokes phenomenon associated to the positive Borel singularity. And it's of this type. So there's a bunch of guys here. Its technical name is Borel residues, but from the point of view of this talk, just think of Stokes data. That's it. Then I have my exponentially suppressed guys, and I have multi-instanton guys. So how do I see this from a matrix integral? Again, this is very familiar calculation, where I start with my cut, I remove k eigenvalues from the cut, and I put them on the non-perturbative saddle. So then I have left with this correlation function of the determinant insertion that I have to evaluate in the matrix model. This is, if you want, the remnant of the van der Maan. And the k guys I took out, now I'm integrating over that contour, the star contour, which goes through the non-perturbative saddle. And I have to do this integral. And okay, and people have done it, and things match. And not only we can match matrix integral calculations to trans-series sectors, but of course, Stokes data comes out for free. The matrix integral computes the Stokes data for you. So how can we, but we know that the trans-series is saying, well, there's more people. It's not only us, there's more. Where are all these other people? So here's a simple illustration of what goes on. So again, that's this is the, oh, sorry, too many. This is the exact integral I just wrote, but where I only removed one eigenvalue, and I keep pressing the wrong button. And so I'm tunneling a single eigenvalue out of the cut, and that's the matrix integral to evaluate. If I want to evaluate, and I'm evaluating the 1,0 sector. The 0,1 sector comes from tunneling a single anti-eigenvalue. I'll show a picture in a second. But I'm just showing the calculation that goes on first. So what's going to happen is that instead of having a correlation function of the determinant, I have 1 over determinant. Instead of doing the calculation in nth minus 1, I'm going to do the calculation in nth plus 1. And instead of, wait, once more. And instead of the suppressed, I have the enhanced guy. Okay? And if I do the calculation like this, and I'll justify with a plot in a second, then the resurgence relations are going to match. So again, what comes out of the trans series, which is the 0 now k sector with exponentially enhanced guys and new Stokes data, the discontinuity at the negative Borel singularity is going to match exactly this matrix integral. Okay? Just to give you a plot of why the n minus 1 and n plus 1, here's the Stokes transition associated to the positive singularity, and what Borel singularity, what I'm doing is just removing an eigenvalue from the cut, putting it over there. That's why I get n minus 1. And then you do the calculation and everything matches. Then there's the negative Borel singularity. There's the Stokes transition in orange there. What am I doing? So I arrive at the cut. I have to create a pair of eigenvalue and anti-eigenvalue. And I move the anti-eigenvalue out into the, so this in light blue is, if you want, the cubic potential of the matrix model. And I move the anti-eigenvalue into the pinch cycle. And that's why I get an n plus 1 there, because I had to create a pair before I can remove an anti-eigenvalue. And if you do the calculation, everything matches. If you try to do the calculation for higher instanton sectors, these are the same plots, and here are the spectral curves. If you do the, so now I'm at L sector. So I already put L guys there, because that's the L instanton. If I want to do what happens, to see what happens going forward, the Borel singularity, the positive Borel singularity, is standard stuff from the literature known for 20 years. That's it. What happens if I want to see the backwards singularity? Well, then I have to create a pair. I remove one guy, then I get the plus 1 there. But there's a little subtlety. It's nothing special. The matrix integral is going to compute the full resonant kernel. Instead of just computing a sector, it computes the full resonant kernel. So it gives you a sum of trans-series sectors and Stokes data. But that's fine. You just compare against what comes out of the trans-series, and again, everything matches. So we're sort of convinced that these eigenvalues and the eigenvalues have to be there. One subtlety in the computation. So here's in green is the cut, and in red is the non-perturbative saddle. Imagine that there was no orange contour, so that there were no anti-eigenvalues. And there were only the blue contours, and I'm computing the discontinuity of the plus and the minus. So this is the standard calculation. I am doing the difference of the C plus and the C minus, and what I get is I grab steepest descent contour, the C star, which goes through the non-perturbative saddle. If you have both eigenvalues and anti-eigenvalues present, there's a subtlety. So what comes out of the matrix model is going to include a pole. And that is basically associated to the fact that now I have the orange contour here, and so I'm going to have a collision of the eigenvalue and the anti-eigenvalue. And so when I evaluate the integral, I no longer have simple steepest descent contours. I also have residue contributions I need to take into account. You need to have a principal value prescription for the integral. Fine. You put all these things on, everything works, and everything matches. So that's just a subtlety. All right, boundary CFT. Can we also do the calculation in boundary CFT? Let's do it in the example of minimal string theory, just because it's simplest. And we've been so far working in the one matrix model, so I'm going to choose PQ 2 to K minus 1. So what do I have? I have a minimum model CFT, PQ as written above. I have the Liouville component, B the Liouville coupling. I have BC ghosts, and I have the requirement of vanishing central charge. So there's a relation between B, P, and Q, whatever. So what are the non-perturbative terms that are at play in this theory that hopefully will match against eigenvalues and anti-eigenvalues? Well, of course, against eigenvalues, it's very well known, but at least until against anti-eigenvalues. So there's basically two contributions. There's the D-branes, and here I am plotting. I'll have to put a couple of plots too, because formula don't completely fit. So here's the disk amplitude of the FZZT. And zeta is the uniformization variable on the FZZT moduli space. And here is just a picture of the FZZT moduli space in the spirit of Seiberg and Sheen. And so I have, this would be the 2,5 minimal string. And I have basically 2 pinched cycles and one cut. What I'm expecting to correspond, because I know that that's what happens with eigenvalues, they correspond to ZZ branes, so I'm sort of trying to figure out what goes on with ZZ branes more generically. And these are the ZZ branes. So the ZZ branes are basically whenever this blue contour, if you want, is sort of closed. And they're labeled by M and N, which are just labeling the pinched cycles. Whereas the FZZT branes are labeled by zeta, which is the uniformization variable. So can I do some sort of computation that will, again, match against matrix integrals and eventually match against the trans series? So it's very famous result that the combinatorics of these D-brane boundaries will exponentiate. And so now I have this ultra curly Z is stuff that I'm computing in the BCFT. So I had Roman Z for the trans series, curly Z for the matrix integral, very curly Z for the BCFT. And that's what I would like to compute with the ZZ branes. That's a hard calculation to do directly because the anomalous amplitude diverges. And so that's a story that we're not going to go into. What we're going to do is to choose a slight detour where there's this famous result that the ZZ branes are basically differences of the FZZTs on the different sheets, and use this to do the calculation because the divergence of the annulus at the level of the FZZT has been regularized by Kutazov and company. So that's the integral that we want to evaluate. So I'm doing the calculation on the FZZT moduli space, and the contour of integration will go through whatever is the appropriate pinched cycle of the moduli space. And then I have the differences. So here's the difference at the level of the disk, and here is the difference at the level of the annulus of the FZZT amplitudes. And we want to evaluate these things. And then eventually via the saddle point approximation. All right, so let's look at the simplest possible example where I have a single ZZ brane or a single negative tension ZZ brane where basically the only thing that the difference is that the contour goes the other way around. So it looks like it's nothing very special. And indeed, if you just evaluate these two amplitudes, it is indeed nothing very special. The only thing that's actually occurring is that I get either a plus or a minus sign. Now, as in the previous case of the matrix integrals, where the fun starts when you start mixing these things, also here the fun starts when I put a ZZ and a negative ZZ brane together. So what's going to happen, let me explain, is that I'm going to have to regularize, there's a log divergence in the annulus amplitudes of the FZZTs that I need to regularize. And when I put that regularization, there's an extra minus sign that is coming from the negative tension D-branes. And what that's going to occur, so here I couldn't put the plots anymore. So the A-1s are the disks, the A-0s are the annuli. What's going to happen is that regularization is going to produce a pole, which we've already seen actually in the matrix integral calculation. So the minus sign of the regularized annulus amplitude gives us this double pole. And now we no longer have just minus signs. Here we just had minus signs, which you'd say that's not very interesting. But the minus signs which are now inside the exponential give you something highly non-trivial, right? E and 1 over E are very different numbers. And so again, everyone matches. So you do the calculation in the trans series. You do the calculation in the matrix integral, using eigenvalues and anti-eigenvalues. You do the calculation in boundary CFT using ZZ-branes and negative tension ZZ-branes, you always get the same results. On top, the matrix integrals and the boundary CFT calculations give you Stokes data. The Stokes data is highly non-trivial, it's transcendental, and it matches everything that's been numerically seen at the level of the transseries. So all these things seem to be making a very tight web of relations. So this calculation matches. We have calculations also in EDS3 and with topological strings I didn't talk about and will not talk about. This was just a plot that I already made, so I recycle it, I apologize. We have eigenvalue and anti-eigenvalue tunneling, D-branes and negative tension D-branes, and Stokes data comes out for free. If you just look at it individually, no.
Then wouldn't the annulus diagram, divergence coming from the annulus diagram be...
The divergence occurs regardless of whether having a negative tension D-brane or not. I'll finish in 5 minutes.
Some D-brane is unstable, then the divergence due to negative tension, the divergence due to annulus is physical, right? You cannot just regulate them away. How do you say, why do you use some regularization procedure to kill the physical divergence? Because what...
No. So the divergence, I mean, the divergence that occurs at the level of the FZZT is regardless of whether the tension is positive or negative.
Yes, I understand, but
okay.
You said that some negative tension branes are unstable, right?
If you look at them individually, that's not what we're doing. We're just seeing what are their contributions to the partition function. We're not stating a negative D-brane in isolation in the world. All right, so I just got the 5-minute warning, so let me just talk about one lingering question. So we have this, if you want, rectangular lattice of transseries sectors, of matrix integrals, of boundary conformal field theory calculations, and you say, okay, fine, but I still have a puzzle, which is what happens when I look at this from a diagonal point of view? Because here, in this main diagonal, I now will have a bunch of stuff which is non-perturbative, well, not that guy is the honest perturbative guy, but the higher guys, which is non-perturbative, but doesn't have a transmonomial associated to it. So what in the world might that be? So let's keep looking at this in the simplest possible example. Again, remember that, I mean, if you have more complicated stuff, this is going to be even dimensional, higher even dimensional lattice. So let's just look at the example where I have A and minus A. And instead of quote-unquote rectangular framing for the transseries, I look at quote-unquote diagonal framing for the transseries. So this is what the free energy would reorganize as along the directions of the kernel. And so I would have, you know, e to the minus n guys, e to the plus n guys, which I'm going to forget from now on. And there I have a purple contribution, which I'd like to understand. Again, the 0, 0 sector is the honest perturbative guy. All the other guys are non-perturbative. Sigma 1 and sigma 2 are the transseries parameters. So they're boundary data from the point of view of the string equation. Now, from explicit data in many examples, this is what those diagonal components look like. And you know, everybody in this room knows exactly what to do if you have something that looks like that. We just introduce an Etoft-like parameter, mu, which takes into account the transseries parameters. And so what that diagonal, which is non-perturbative from the point of view of the string equation, is spitting out is a perturbative expansion of some other closed string theory where the transseries parameters have been upgraded to some sort of topological string background moduli. So this is actually both generalizing and explaining something that was sort of in the literature about 7 years ago, the Pain-Levé gauge theory correspondence, where Pain-Levé equations were giving rise to specific dual partition functions for Argyrius-Douglas gauge theories. Well, for their prepotential, and then you would get, you know, the whole higher FGs on top. So now we both have a physical explanation of why that was true for Pain-Levé equations, because we have these eigenvalues and the anti-eigenvalues, or because we have these D-branes and negative tension D-branes. But this is actually a very big generalization, because this is no longer true only for Pain-Levé equations. This is true for anyone in the multi-critical hierarchy, anyone in the minimal string hierarchy, in fact, any topological gravity, or any Hermitian matrix model. On top, we get a couple of things which come along. From the direct resurgence of the original problem of, let's say, the resurgence and relations of this quote-unquote rectangular framing, what am I going to get for this diagonal theory? I'm going to get the standard resurgence of the string theoretic expansion, because I do have the string theoretic expansion with a modulus, so it's a little bit more intricate, but it comes out for free. And we get wall-crossing formulae for the prepotential of the Argyres-Douglas theory. So how do we do this? I'll meet for 3 minutes, if that's fine. Okay. Sorry, Edward.
I also think that this is a renormalization of these strings.
I'm not sure what does the word renormalization means in this context. So we have a conjecture for what the full result that comes out of the trans series would be. So that's if you want, the resurgent trans series associated to the string equation, which comes out from a one-cut problem. And we're saying that that can all be repackaged. That's actually a mess when you write down the trans series, as I showed a couple of slides ago for the specific heat. That can be repackaged as a discrete Fourier transform of this type, where I have, let's say, quote-unquote, the Fourier kernel. Let's not worry about that. And what I have inside is a two-cut free energy, where, so if I had my Ponlevy problem, I would have my semi-infinite cut and my pinched cycle. And now I'm not moving away from the double scaling limit. I'm just opening the pinched cycle according to mu. So the boundary data, the trans series parameters, are opening up this pinched cycle. And then I have a two-cut problem there, which is perturbative. So all I'm using is the perturbative expansion of that free energy. And if I just plug it in like that, I get the full non-perturbative answer. By the way, this involves not only reconstructing the trans series, but also uses Stokes data. So I can't write down my little row guy there unless I know Stokes data. So I didn't speak about Stokes data, so you may ask, what are these functions? This is just a generating function of Stokes data. Let's leave it at that. Stokes data is needed in order to do that. And so the punchline is that the two-cut problem compactly rearranges the one-cut resurgent trans series. But it's the perturbative two-cut problem, which is rearranging the full non-perturbative answer. All right, and this gives us a cleaner organization of this main diagonal of the trans series that we were just discussing before, of these people here. Because now I can see what goes on in examples. And so in the usual example we've been discussing, the main diagonal, that guy there, is reorganized into the Argyres-Douglas. So basically the 2-3 minimal string, which is the Ponlevy 1 problem, gives rise to the A1, A3 Argyres-Douglas theories. And you can do this generically. So you can use topological gravity where you have your KDV times, they're sort of free, and they're giving you the moduli that you need to construct the let's call them the odd Argyres-Douglas. And you can use the Hermitian matrix models to construct the even Argyres-Douglas. And as I said, on top for free, you get the resurgence of these two problems. So basically, this is the original trans series. So there's a row 0, which I have been putting along. I have left under the rug that you also need a row pi, because there's basically the discrete Fourier transform looks slightly different if you do it on the positive singularity, on the negative singularity, but I mean, you know how to map from one to the other, so that's not the big issue. And out of the resurgent relations that you know for this problem, you can predict the resurgent relations that come for this problem, and for the Argyres-Douglas side. And there's two types. So there's the standard resurgent relations that are discussing how the string expansion is going about, and there's basically walls of marginal stability that are also coming out for free. So where are they coming from? They're coming from the fact that this two-cut perturbative free energy needs to be regularized when you put it in, which is associated to the shrinking cycles that you have. You have to put an explicit Barnes coefficient there, which is associated to, if you want, a Gaussian partition function or a conifold point. And then this gives rise to a conifold singularity on the Borel plane, and when the conifold singularity crosses the standard singularity of the in this case 2,3 problem, then you have, you know, a higher order Stokes phenomenon, so you get the wall of marginal stability. All right, so I think my time is up. So let me end with one final question, which is how generic is this story? So hopefully in this next 2 weeks I'll be around. I'll be getting feedback from some of you if this is worth exploring in harder examples or not. Thank you very much.
about this positive exponent, when I'm comparing this quantum mechanical example, which you know very well, right? That there on the
Which
first
example?
Sorry?
Which example that I know very well?
A quantum mechanical example.
Okay.
So, where you have this exponential contribution and all this stuff. Long ago, it's kind of goes back in 60s. This exponential contribution as function of Kaplan constant exponent -1 over g square on the first Riemann sheet, right? But it's essential singularity, so there is, of course, there is a positive on the other sheet, right? And when you have, in your example, what you're talking about, when you have this different sign of the exponent, is it kind of in terms of this interpretation, physical sheet?
Yeah, so what I would say is that the plus and minus that you see in quantum mechanics are coming from just using the exact WKB methods, right? Yeah. And here what we're doing is we're doing the partition function. Were you to be looking at wave functions in these problems, you're also going to get the plus and minus, but you're going to get the plus and minus of the exact WKB, which are associated basically to SZT contributions, and on top, you're going to get the plus and minus of the ZZ contributions that I was talking about.
I have a question about the matching of the one instanton effect in the matrix integral and the string equation. So if I understand right, the 1,0 instanton in the matrix integral arises from integrating an eigenvalue in the forbidden region outside the Kavli, right?
Yeah.
What is the matrix integral? And so that working that out gives you this formula that you computed with the.
Is this the one you want?
Yeah, so the top line I understand could be derived from that perspective. What is the matrix integral derivation that gives you the middle line?
The second line?
Yeah.
Okay. Give me a second. I have some extra slides. This is the matrix integral derivation. So basically, you use the involution map to move from the physical sheet to the non-physical sheet. This is how the involution map acts when you're moving between the two sheets, okay? And at the level of determinant correlation functions, we prove this equality, which is basically what gives rise to what you're asking. So here you have the involuted guy, So this is the tunneling of the eigenvalue into the involuted sheet. And you can show that once you do the calculation in the involuted and you bring it up to the physical sheet where you want to evaluate your integral, this is what comes out.
I see. So it's a eigenvalue in the forbidden region, but on the unphysical sheet.
Yes, that's right.
Okay, I have one other question.
Okay.
In the matching to the D-brane calculation,
yes,
the annulus diagram connecting the ZZ brane to itself is divergent and requires this string field theory discussion.
Yes. So if you're asking how to do the calculation straight off with ZZs, we don't know. That is, has been done by Ashwaksani in string field theory.
Okay. Yeah.
So what we're doing here is just doing the calculation using the differences of the FZZTs.
Thank you.
Thank you.
Thank you for the talk. I have a quick question, maybe vague, but do you have any speculation of what would be the interpretation of this diagonal reorganization, say in type 2B string theory, the instantons or something like that?
No.
Okay.
That's what I hope to get back from this program is what should we do outside of this more random matrix kind of example. So I have no idea. So what you could ask is, if you're looking at generic string theoretic systems like ADS-CFT or whatever, is this a sort of a rectangular theory or a diagonal theory? I have no idea. Sorry.
Can I ask?
Sure.
Could you explain what you? I think I didn't understand your terminology of Argyris-Douglas theory. What did you mean by that in this context?
So in this context, where is it? Here. In this context, all I mean is basically, if you will, an n equals 2 supersymmetric gauge theory at the conformal point of the Seiberg-Witten moduli space, where basically I can still use the matrix integral spectral curve, if you will, but the differential is no longer the Seiberg-Witten differential because we did a scaling, and now what I have to do is just a standard matrix integral differential. That's the Argyris-Douglas theory.
Sorry, what is the observable that this string...
Partition function.
Of what? From the gauge, n equals to gauge theory language.
Oh, I'm computing the prepotential. So F0 is the prepotential, and then I have the topological string corrections on top of it. That's it. We're not doing any other observables. So maybe we'll try, but we haven't tried yet.
But is there a direct interpretation in the string theory language? In what sense is this mu a deformation?
A deformation?
I thought you wanted to view this as a...
No, I see it as a modulus. So the boundary data has been operated to a modulus on the Argyris or the topological string side, maybe to be slightly more correct. That's what I mean.
So in the phase of the theory when G string has a positive real part, one would have expected that the negative action instantons would lie outside of your physical contour. Is that captured by what you did, or do you find otherwise?
So when you have these parameters, maybe let me just, when you have this trend series with sigma 1 and sigma 2, they don't need to be turned on all the time, right? If you just want to start in a phase where all you have is a perturbative theory, nothing else, just set sigma 1 and sigma 2 to 0. And then you're fine. But then as you move around the complex plane, there's Stokes phenomenon, and that is when these people start getting turned on. So, I mean, what I'm doing here, if you want, is from, what, quotation marks, non-dynamical, right? I'm just seeing what is all the structure that comes out when you have both sigma 1 and sigma 2 turned on. You could then ask a different question, is what happens as you move along the different phases that the matrix model or whatever system may have. Then you do have phase transitions, which are accounted for by the sigma 1 and sigma 2. So you could have regions where you have only one cut, you have regions where you have multiple cuts, where you have eigenvalues organized in trivalent regions, and this is accounted for by Stokes phenomenon as you move across the phase boundaries, and describes basically, if you will, the eigenvalue distributions of the matrix model in the full Etoft phase space, let's call it like that.
So you're not sticking to a particular contour when you write down the trend series.
So when you allow sigma 1 and sigma 2 to be whatever, it's like you're allowing all possible contours. Then you can have 2 points of view. You say, well, I'm just looking at the canonically favored contribution and study how eigenvalues organize, or you just say, no, I don't care. I just look at everybody at once and I see what the structure is. So I think it's both points are fair.
That was very nice. This is probably in some of your papers, but I was wondering if there's a quick summary of what happens in the large P limit if you were trying to take some of this diagonal structure to understand JT gravity.
Right. So that we don't know. So one possibility you could ask is what happens for JT gravity when you start doing this diagonal analysis. So we have a guess. I'm not sure I should say because it's recorded. Oh, I can say it. So there's this Douglas Schenker study of the n to infinity limit of Seiberg-Witten SUN theories. So our guess is that if you look at the Argyris-Douglas points of this series, that's what it's going to be. But I don't know. So let me also say, because it's being recorded, I don't know.
Let's thank Ricardo again.
Thank you very much.